So if you've downloaded the code from the GitHub, maybe not all of you have the link. If you know the link, you could maybe share in the chat for anybody who doesn't have it. What I've done is I've created two pieces of code for today's lecture. One of them creates a pass heat map, and the other one tries to do a more statistical comparison of that. We'll come back to that. Let's just look at the pass heat map one. Basically, we say the team that we're interested in and load in their data. We've done that in some previous things. Here, I'm just trying to find the match ID. We've done that in previous things as well. And so what I do in this loop here, just expand that out a little bit so you can see. What I do here is I have a loop where I loop through all of the matches that we're interested in. Just to be clear, this is the code that we're going to use to generate the heat maps of where the players have passed the ball. So I load in one at a time. I load in each of the files. I find all the passes for that particular match. I find all the shots in this particular match. Then I set a window. So here I identify shot times. This is the times of each of the shots in the match in seconds. So I multiply the minutes and I take the shots in the match. Then I have the shot window, which gives us all of the, it gives us 15 seconds back in time. Then I look at shot times minus shot windows, and then I look to see that the passes in the match are correct. I've an awful feeling when I just looked at this just now that I might not have taken account of the different halves of the match. I'm going to look into that as soon as I finish this. So please note that this this has now just occurred to me right now while I've done this. I haven't adjusted for the different half of the match, which we'll certainly have to do. But I will go back and check that afterwards. And then what I've done is I've used a function here which looks for the looks to see if a pass has happened within a certain time. So it's here which finds if the matches have happened within the last 15 seconds. I apply that function to all the shots, and then I find out which of the passes led up to a shot. I eliminate the corners, and then I call all of these danger passes. And so this whole code here picks out all the passes, all the dangerous passes leading up to a shot. And we run that, and we go through each of the matches, and we find out how many passes there are leading up to a shot in each case. And once I've got them, I can do the main thing here is finding the X and Y position. So first of all, I just plot all of the passes. This is the one which makes the plots of the passes. And that produces this plot here. And then the next thing I do is I make the histogram. So I'm just going to make X and Y positions of all of the passes. That's what this bit does. Make X, Y positions. And then I use this 2D histogram function. Now this is basically the crux of making a heat map here, is that you decide the number of bins. I think I said 5 was the optimal here. You have the pitch, the size of the pitch, then you put in the X and Y coordinates, and you see they're reversed order for the Y and the X. Again, this is something you find out from playing around with the histogram function, is that you can make this histogram. So this is a sort of key function which you need to use to make the histogram. And then we plot our histogram. So those are the steps in the code for making these things. Good. Gonna have to come back and check that I have got all the passes right, because I'm not used to using StatsBomb data. I'm not sure that the times are right for the two halves, but I'll check that afterwards. Okay, so now going back to the presentation. What we still haven't done is we still don't have a statistical understanding until we compare all of the teams. So one of the plots that I make, and I'll go to the code to this later, this is in the part 8, is I look at the number of passes made by a team against the number of shots. So I have shots on the x-axis, and I have a number of passes on the, shots on the y-axis, and I have number of passes on the x-axis. I think I've forgotten to label these, but I've got 0 up to 40 is the number of passes, the number of shots, and then I have number of passes on the x-axis. And the question I'm interested in here, is there a relationship between the number of passes a team does and the number of shots they have? Which is very related to the counter-attacking question that came up. Are teams which pass the ball more successful in generating shots than teams which are very counter-attackish and don't make many passes leading up to shots? And I've got all the data from the Women's World Cup, and this is, each dot here relates to a particular match. Now, how am I going to test this relationship? Well, I'm going to test this relationship using linear regression. And the way to, how linear regression works is it minimizes the sum of the distance between the points, here are all the points, and the best fit line. So how do I best draw a line through this data? I think we can probably see that we expect a line to have a positive slope here and not to just be flat. But how can we test that the best relationship between shots and passes is a positive line? Well, what we do is we minimize the sum of the distance between the points of the line. And I do this in one of the video lectures as well and go through the basics of doing this, but the basic of fitting linear regression is this minimization of the distance indicated here in the red between the points and where the line is. And the line, if this line has a positive slope like this one does here, then there's a positive relationship. If there's no slope, if it's just a straight line across, then there's no relationship. And if there's a line going down the way, then there's a negative relationship. So we minimize this sum of squares, and then we look at what relationship comes out in this line. Okay, so here is the line we get when we do this linear regression for shots and passes. And we have got a positive line going up through the points. And so this is the best fit line. So if we minimize all of the distances between every one of these points, so we sum all of the distances, we square them, and we find the minimum, this is the best fitting line to that. And that's basically what linear regression is. When we do the analysis, here's the statistical analysis that comes out. Again, this is in the Python code. We find that the intercept, B0 in my line here, this is the equation for the line. Now B0 plus B1 times the passes is equal to, it's actually shots in this case. This is the relationship that I'm testing. And I look to see what is the intercept of this line, and the fit tells me that the best fit has a coefficient of -4, so it's somewhere down here. And B1, the slope of the line, is 0.03. So for every pass, there is 0.03 shots in this line, so it increases like this. See, the intercept here is below 0. And how do we know this is the best fit? Well, we can use the p-values here for the fit. We're testing the null hypothesis that the line has slope 0. It would look like this, and that the intercept is 0. And I think we're most interested in the slope of this line, and it's got a slope which is significantly different from 0. We have a p-value that's very, very small. Often use p-values of 5%, so 0.05 here as some sort of test, but it's much, much lower than this. So then we know that there is a positive relationship here. We're also interested in the r squared. The R squared is basically the total sum of, is the sum of squares we get from these distances to the line. This I've taken from Wikipedia, but this is the distances to the line, sum of squared, plus the total sum of squared, which is the distance to the average of the data. 1 minus that difference is the R squared, and this measures the degree of fit. So it gives a number between 0 and 1. So 0 is no explanatory power of the model, and 1 is that it's a perfect line through all of the points. And so here we've got around, well, we've got around 50%, 0.46. And so we've got a reasonable fit, but not the most amazing fit in the world between what the model predicts and the data. So R squared is probably one of the essential things for goodness of fit. Two things I'll emphasize, I'll go back and say this, that emphasize that we have B naught, which is the intercept. We have the parameters, then we have the probability of fitting. These are very important. And then the R squared then measures the goodness of fit when you're doing linear regression. And it tests the null hypothesis that the intercept B naught and the slope B1 are 0. And our test says that we can reject that null hypothesis, and we think that a positive slope relating these two things. Okay, can we learn something about the individual teams? And what we can learn is this, the USA, for example. So what I've done is I've colored in red particular teams we're interested in. USA, I think this is their match against Thailand. They have lots and lots of shots and lots of passes when they really dominated this match. But you see that USA, who I thought were a heavy possession team, sometimes they had less passes in a few of their matches. Some of their passes, I think, against matches against weaker teams, they really dominated, had lots of passes and lots of shots. But they very typically follow this relationship, actually. Maybe a few more shots than might be expected, but they're quite well representative of this relationship. On the other hand, England, they actually have fewer shots than you would expect given the passes. And again, this relates down to what's the most effective style of football. And England are clearly playing lots of passes, lots of possession football, but they're actually managing to have very few shots based on those, or less shots than you might expect based on those passes that they've got. So they're you can say underperforming in this particular chart. Given that they're playing a possession style football with lots of passes, they're having fewer shots than we would expect them to have. And I think that's an interesting point about England, and something which we're going to raise later when we're trying to analyze how they've been performing. Linear regression, really important. It's basically a quick way of checking if there's relationships in the overall data. Now, we might take it for granted that the more passes you manage to have, the more shots you have to have, but that's not necessarily something we should take for granted. In general, the amount of possession teams have in football isn't always reflective of their expected goals or their real goals. So linear regression is a quick way of checking relationships in data. Here's some examples which I take up in some of the other lectures. This is an example from Michael Cayley, where he is interested in how well expected goals predict future goals. So what's the, if you have the goals that teams have scored, if you have the shots on target that teams have scored, if you have the expected goals the team have scored, how can you predict their future goals? And he found that the correlation, he used the R squared, was better for expected goals than it was for either of the two other measurements. And that's one of the reasons, and this is a repeatable thing you see quite a lot, that's one of the reasons expected goals is a better predictor of the future goals than the goals themselves are, or shots on target are. And that's basically why bookmakers use these expected goals models, because they are more like they're going to have a better understanding or a sort of edge over any punters who are using the performance or the goals of the team. So expected goals just give this small edge, small predictive power that allows you to make better decisions. Next, I mentioned this with possession. This is a study I did a few years ago now, where I just looked at the mean goal difference of matches and I plotted it against possession. And I did this for the Premier League season 16-17. You can try this for some of the other leagues. Excuse me, I have to cough. You can do this for some other leagues. And what's very interesting here is that it's quite flat, actually, this relationship. So there's in fact, there's no relationship in this data. There's no correlation between the mean goal difference in matches and the amount of possession teams have. So although it might seem obvious that this passes and shots should be correlated, goal difference and possession is not typically correlated. Sometimes it is in football, sometimes it isn't. In Premier League 16-17, it wasn't. And in the Champions League, it was slightly correlated. So there's a slight line there. I've marked in here, for example, Barcelona, who always have a very high possession style of play and are quite successful. Well, they were in that Champions League season, but the general tendency is reasonably weak here. There are some teams which play possession football. Bayern Munich were also the same in this particular season. Very successful teams that play possession football, but possession is not a very good predictor of football. I often say that one of the reasons you see when you're watching TV, and you also see this a lot on bookmakers' sites, they tell you the possession statistic. And that's because it's a misleading statistic about the match. So if they want you to bet more on particular teams, they'll tell you they have high possession and you think that they're doing well. But possession isn't in general a very good statistic for predicting that a team is doing well. Teams that are under tend to have the ball most because they're trying to catch up, but then they become vulnerable to counterattacks. So there isn't that very clear relationship. Possession and winning are not usually, let's say, they're not always correlated, is probably the best statement to make there. So for goals, I'm going to go into this more in lecture next year. You'll notice that I did shots here rather than, I did shots here with my fit rather than goals. And there's a reason for that. And that's because when you do goals, you shouldn't use linear regression. Goals are very rare. So you should use something called Poisson regression. And we're going to come to that in the next lecture. But for those who are wondering, I actually do a Poisson regression in the Python code. And I find that there is a positive relationship between goals scored and the number of passes made. So there is a relationship you can find using a Poisson regression fit. In the next week's lecture, next week's Tuesday lecture, I'll go in and explain what a Poisson regression is and why we use it for fitting for goals. The basic reason is there's very few goals in football, and so you have to take that into account when you're doing your fit. And goals tend to come up as random, so they're better modeled by a Poisson model. Okay, let's have a quick look in the code again then. And I will now go through this code, the pass compare part, just loading in the data to start with, the normal types of things, finding the matches that we're interested in. And then I'll run this and then explain it during the time I'm running it. What I do here is, so in order, what I'm going through now is how I made the plots that I just showed you, looking at the relationship between passes and shots and goals and so on. What I do is I go through all of the matches and I create a new data frame with the team that they had, the passes they had, the shots they had, the goals they had, the danger passes they had in various different situations. And once I've collected all of those things together, I'm going to do two things. I'm going to plot them and I'm going to fit the statistical model. This is the model here. and I first plot everything up here. I'm just running through every match now, finding the number of shots, finding the number of passes, and so on. Some very good discussion in the chats while doing this, looking at about the expected goals. I'll try and come back to some of those questions at the end, because I said I'd say something more about expected goals. My computer is slowing down trying to stream on YouTube, do Zoom, and run these things at the same time. But okay, we've got the passes. So this is the code then that makes the plots I did. This was the England thing here. Down here is I import the stats models. This is something which caused me all sorts of problems, is that you have to convert everything to numerical data in order to use the library. You see here, I use the stats models library. Now there is another library, which I've forgotten what it is, which is more commonly used for machine learning. So this just, in a way, this shows a little bit how old-fashioned I am. I prefer the stats models library because it does statistics in the way that I'm used to doing statistics. But there are different libraries in Python. I mentioned this a bit in the expected goals lecture for doing this type of thing. And what's done here is I've run the logistic regression. That's the one that I showed you on the screen. It does this nice summary with everything you need to know. Again, I'll just emphasize R squared is one of the most important things. BIC, that's something actually that's AIC and BIC are important in the logistic regression, in the expected goals logistic regression type of things. But they're just now, when we're doing ordinary least squares, R squared is the most important point. Then we have the coefficients that we get, the passes. And then I take the code, B is the model fit of the parameters. So if we look there, we have minus 4.736, we have 0.038. When I set B equal to this, I have those parameters are put in there. And then I can plot the line fitting to the figure that I've got. I'll just do everything here again so we get the whole figure up. And we get the figure with the line in it, and we get the dots. So again, this is something which, when you're playing around with data, I think it's always nice to just be doing a few of these regressions to try and work out what's going on and find out, in this case, I've even got the y-axis here now correctly, find out how these things, what types of relationships we expect to have. Here's the Poisson model, same thing. I run this here and I get the B parameter values for that. Didn't give me a summary. Just do that again so I get the summary. And we get the summary here. Again, there's no R squared for a Poisson regression. You'd usually use the log likelihood to see how good the fit is. But I'll go into that again when we look at the Poisson model in future lectures. Okay, and then finally in this, this will be the last thing I do in the lecture. So that's it, all the code you need to make how I've shown you to do the linear regressions and so on. Then the last thing I'm going to do is I'm going to make a team comparison of these heat maps. So I mentioned that a weakness of what I did before was that it just tells you the number of passes of the different teams. It doesn't compare it to the average team. So it might be that, especially when it's attacking right and left, might differ between the teams a lot, but where you attack up the field, which teams are counter-attacking teams, which teams are possession teams in the final third. And here it creates every team and compares them now with -3 and 3 is the scale here. So I've used a red to blue color scale, mainly because I want 0 to be neutral. So if you're exactly the same as the average team, you have 0. So here on the pitch, France are pretty much equal to an average team in terms of how often they pass from that area. Again, in the 15 seconds leading up to shot. But up here in the final third, France are above average in the number of passes they have here. And so that's an interesting clue to see that, well, France are good. They've got the ball a long way up, but also they're going to attack possession in the final third or in the final fifth is a big part of their game. And you can compare to different teams here. Nigeria, rather unsuccessful in having passes further up the pitch. Little indication, a few more longer passes there. This is Netherlands attack a lot on the right. Chile, so Chile attack less in the box, but they're very successful of making passes from the midpoint here. So they begin their attacks further back. Same with Cameroon, again, more than average passes over here. Japan attacking on the left more than on the right. And this can give you an overall view. I mean, I have to admit, I'm no expert on the Women's World Cup and the different matches, but it gives you an overall view of the different teams. And now I come up to England, which I'm going to look at finally. Good, so I'll go back into the PowerPoint here. Difference to average of all the teams. So this is England's women's team, more passes on the right-hand side leading up to a shot. Okay, so based on 3 or 4 hours data analysis, and I had this kind of nightmare here that I might have done something wrong with the minutes of the match. I'm going to have to check that afterwards. I will update it and tell you if I have got that wrong. I'm sure somebody in the chat has already spotted if I have got it wrong. But I think these were the 15 seconds leading up to a shot. What could you actually say about England? Or if you were interested in the, it's interesting, in Sweden, there's the playoff for 3rd or 4th place is a big thing in all sports. So they call it the bronze match. English fans seem to be less interested in this game, but Sweden met England in the 3rd, 4th place playoff in the World Cup, which is a big game for Sweden. England tried to downplay it, but what could you tell England or Sweden about the teams leading up to the World Cup? Well, I think there's 3 things that are interesting to present here. England do seem to have a lopsided attack where Lucy Bronze is very important in terms of the passes that lead up to dangerous shots. So she's their key player. And in lots of other rankings, I've checked this up, she's top of a lot of rankings for creative play. So Lucy Bronze is the person to worry about, and attacks down the right-hand side are something to worry about. Fran Kirby is the forward, and she's the one who's responsible for all the passes in this area. So those are the 2 key players to look at, with attacks mostly coming on the right. One thing that does seem to be the case, and that's what the statistical analysis brings out, is that England aren't actually getting to shots as much as you might want them to. So they're doing a lot of passing, a lot of build-up play, but they're not always getting to shots. And this is something to think about possibly as a negative feedback for Fran Kirby, who's playing in a forward position, passing the ball quite a lot here, but they're not getting to shots as much as they could. I think this has to be qualified. We'd have to look at the expected goals to see if they are actually generating higher expected goal chances, but they're not managing to produce as many shots as the opposition. So that's a quick analysis of what's going on inside England as a team. What I want to emphasize, I'll just answer any questions before I give a summary of everything. So if I stop the share there and I open up here, any more questions that I can answer? I'll go back and have a look at a few of these expected goals questions. most of these questions I see are about expected goals. Let me just use the last okay. Here's a question. When you're running these kinds of models, do you consider a pass in the final third and a pass in your own third as having the same importance? The answer to that is, well, no. A pass in the final third has more importance than a pass in the first third. One way that you see why that is the case is going all the way back to this figure. When I showed you this, all passes by England's women in the World Cup, you see that lots of passes occur here in the first third. But when we move on to passes within 15 seconds of a shot, you see that all of the passes, most of the passes are up here. And so this means that these passes are more important and are dangerous. Again, I'm going to emphasize this point is that the value isn't something that comes out of the value I put in this statement isn't something that comes out of the model. It's not the model that tells us that. It's our understanding of football. We know that it's more dangerous in the a pass in 15 seconds coming up to the shot must be more dangerous. So we know that, and so we can see that these types of passes have more value than passes further back the build-up stage because they're not likely to lead to a shot. But one thing that's important, I want to come back to time after time and time again. In the other lectures in this section, I go into the expected goals. What I'm trying to do here is build up a statistical understanding of how the teams are playing rather than put too much value in any one of those actions. I thought about Ben asked if we can show about Hammarby. I thought about that, but I haven't asked permission for anybody to be filmed, so I'm not going to show you about Hammarby, around Hammarby, I'm afraid. Okay, good. Hopefully I've answered the questions I've got there. What I'll do in the last section is just say a few more things about expected goals. So please put in your expected goals questions into the chat now if you've been looking at the other lectures, and I will go over to the expected goals presentation and say a few things, but I'm not sure if I should concentrate on the start of how expected goals works, or if I should go into more detail. I'll see which questions you give me, but I'll start by giving the basic idea of expected goals. New share. Okay, so I think that this figure, and it comes up a lot of times in the presentations I do, this is the key idea of expected goals. The idea is that some places on the pitch and some types of shots are better than others. There's a higher chance they result in a goal. And this is shown in the following plot. This is the probability of scoring from different areas. So 7%, everything within this circle has a 7% chance of being a goal. Everything within this circle has or this shape has a 15% chance. Everything within this shape has a 30% chance of being scoring. So not all shots are equal. Some are better than others. And the reason we know this, and this is the details I go into, is that we have fit a statistical model over all the shots that have occurred, and we look at the probability of scoring of those shots. And this is the functional form that we come up with when we do this. And there's lots of questions. Well, you know, somebody might score from here or they might score from there. That doesn't totally invalidate the model if particular goals are scored from particular places. Sometimes people score from all the way out here. What it tells us is that statistically, those shots are less likely to be goals. And now if you're a team who are producing lots of shots from in here, then in general, you're performing better than a team which is producing lots of shots from further away. And one of the key consequences of this is that, and this is reproducible match over matches, and one of the key consequences of this for a striker is that you should measure yourself not only in how many goals you score, but you should measure yourself in terms of how many times you're getting in good shooting positions. And that is how much expected goals you're generating. It is actually harder for a team to find themselves in good shooting positions more often than it is for them to actually finish those positions. And that's a statistic that I mentioned for the Michael Cayley thing, that he's found that expected goals is more reproducible than goals themselves. So strikers will possibly have a sort of blank spell where for 5 goals they don't score. But if they are getting into lots of chances, then the chances are they will start to score into positions for lots of chances. The chances are they will start to score in the future. And this is a statistical pattern we see. So that when strikers aren't scoring, there's 3 explanations. One is that they're having bad luck. One is that they're not very good at finishing. And one is that there's something wrong with the expected goals model, that actually the teams they're meeting are filling the penalty area, for example, and not the chances look good in the model, but they're not really that good. It's very seldom the second one that is the explanation for why a player isn't scoring for a long time. The other explanation that they're having bad luck, there's lots of randomness in football. Maybe the goalkeeper went the right way and so on. They just sliced it slightly. That's a more likely explanation. Or this third explanation that teams are doing something tactically. Burnley are a good example of this, for example. Teams are doing something tactically which reduces the quality of the chances. So that's the basic overall idea of expected goals. Go into the lectures and you can get more of the details of these particular models. There's a question here. Could one say that comparing team 1's expected goals with team 2's expected goals is a more statistically good way to pick the best team of the match than comparing the teams over the goals? That's a really good question. The answer is, over one match, no, it isn't very much better. So I wrote an article. I'm going to copy and paste the I think I am sharing here. So I'll just show you here. I wrote an article here, and you can go in and have a look at it. I'll put the link in there. Whoops. Well, I'll put the link in later. This basically tells you the number of matches and what you should use to compare. So I say that maybe over like 3 or 4 matches, there is actually no real way of knowing how well a team is performing. This sounds quite crazy, actually, given that almost everything we ever read about football is over one match or 1 or 2 matches. But there's so much randomness in football is that you can't read very much into 1 match at all. You can't even read so much into 3 or 4 matches. So it becomes after 4 matches, there's sufficiently low amount of randomness in football that expected goals start to be the best way of seeing it. So I say between 4 and 6 matches, expected goals are the best measure for comparing 2 teams. Then once you get between 6 and about 15 matches, expected goals and real goals are both useful. Then after 15 matches, goals tends to be the better way of assessing the quality of the team. So that's the answer to that. Mark asks, on calculating the percentages in the first place, how are deflections by opponents or teammates? Deflections are so there's always lots of different models. I think we would call, in most cases, if the I'm a little bit unclear if this is a deflection that goes into the goal or a deflection that doesn't go into the goal. If it's a deflection that goes into the goal, it tends not to mean very much. So we just accept that we accept it as a shot that went into the goal. And so they're just fitted in the model. And so we don't take account of it in that case. If it's a own goal, yeah, I think that's probably the best answer to that thing. It's not the sort of thing that we take too much account of in an expected goals model. It's if the shot in the end ends up in the goal. John Lindblad asks, I realize it's very difficult to do in practice, but do you know of any work done on non-shot expected goals or other ways to evaluate opportunities that doesn't end up in a shot? That's a very good question. The one common way is just simply how often you get the ball into the danger zone. And what I mean by the danger zone is maybe the 7% circle. So if you said number of times I get the ball into the 7% circle in a match is a very good way of evaluating, almost as good or possibly better than expected goals, how well you're performing. Rodrigo says, how can we use expected goals info of a match to calculate victory probability? That's a really good question. That is exactly what I'm going to do in next week's lecture, where I look at Poisson models and simulations. I'm going to show you how you can convert an expected goal into probability of different results. Do expected goal values consider defending position? That's a really good question, which I'm going to tell you the answer to here. This is an analysis done by Jerne, who's in Slovenia. And actually, after this analysis, he did such an amazing job on this. We actually hired him in the company I co-run, 12, to do analysis or for a television company that we work with. And he did this thing with StatsBomb data. He basically counted the number of defenders within the shot zone and used that in the model. And so you can see in this particular case, he looked at the number of opponents, which is 3, and that would reduce the goal probability because there's 3 opponents in the way. Here, where you have the sort of half opponent in the way, then well, it's maybe half opponent, then the goal probability is smaller. So that might actually be the goalkeeper being in the goal, is that thing. So yes, you can exactly do that. You can put it into your logistic regression model. If you follow the instructions for the logistic regression model, you can put in this goalkeeper into the logistic regression model. Good. More questions. Joseph asks, how does the expected goal model handle block shots that doesn't reach the goal or the sideline? It tends to handle them in the way it handles all shots. Either it goes in the goal and you give it value 1, or it doesn't go in the goal and you give it value 0. So a block shot is a missed shot. So it does put them into the model, and the fact it's not a goal means that it reduces it. You adjust the probability in that way. So you can make different types of models where you account for these block shots, but generally it just means that it's not a goal. Great. I think that I've covered most of what I wanted to cover today. I think maybe I'll just go back and I'll have some sort of closing words on this. So closing words, and I emphasize this quite a lot, and also in what I've talked about today, is that it's worth thinking of yourselves. Of course, you're data scientists, but it's also worth thinking of yourselves as data alchemists in this case. And I like this phrase a lot because it gives a sort of slightly less scientific view of what we do in our jobs. It's nice to appear professional and to claim that we're scientists in everything we do. But actually, the way that you should work with this football data is you should think, what types of insights can I get from it? And you should compare it to the traditional insights you get from journalists writing about football, you get from coaching staff, you get from your own experience playing or watching football. You should use it as a way of complementing that. So I don't want to give the impression ever that there's a sort of final answer of some mathematical model, be it expected goals or anything else, which solves all the problems. There's never a final answer. Instead, it's you interrogating the data, learning about the data, and getting better at understanding how you can use the data in different things. So I very much emphasize this data alchemy type approach. And I do think there is a certain way of thinking, and I don't know if this is just reflective of my own way of thinking, but I think you should always go into these problems with a certain arrogance about what you can manage to find out from the data. If you learn about the data, you'll be able to find something different and new out about that data. But once you've done your analysis, you definitely need to have a certain amount of modesty in what you can then say to football coaches or experts. So you often can't manage to say to them anything that they don't know. If you take my England analysis here, if I told the England coach that you attack more on the right, then he'd say, yeah, of course, we attack more on the right. That's been a thing and it wouldn't be something that Sweden didn't know either. So you should be very modest about what you found out in the end, but go into it with a sort of positive attitude. Maybe arrogance isn't the right word, but a positive attitude about what types of things you're going to find out from data. Plot things, make pictures, do statistical tests, be rigorous in doing those statistical tests, look for unexpected patterns, and try to build up a picture of what's going on that aligns with your football knowledge. And more than anything, when you're doing these types of analysis, just enjoy yourself, enjoy looking at the data, enjoy trying to build up this type of understanding, and enjoy building up these types of analysis. And if you're enjoying yourself, I think it's like playing football as well. If you're enjoying yourself, you tend to do things which are more creative and better. Okay, that's that for today. And the tutorials will be on Thursday for those who are in the course. There is an amazing amount of stuff in Slack, which I'm really, really grateful for. And I'll try and go in, definitely on Thursday, I will go in and go through Slack and give some feedback on that. For the people who are doing the course properly, you're not posting as many things as the people in the Slack group are doing. So you can certainly post your things before Wednesday, and then we will talk about them at the tutorial on Thursday. We're going to have one more guest lecture, but it's not going to be live. So it will be recorded. Then next lecture I'm going to do is I'm going to look at the Poisson model and how you actually simulate a football match. So until then, have a good week, and I will see you either on Thursday or next week. Thank you very much.